Let's talk about the combustion of natural gas. Natural gas is methane. This is what is pumped to your house in pipes. Methane gas is one carbon with 4 hydrogens. Again, this makes sense because carbon wants to have 4 bonds. Hydrogen wants to have 1 bond. And so here, carbon has its 4 bonds. Hydrogen has its 1 bond. Clearly, methane cannot react by itself. Methane wants to produce fire. And so it needs oxygen. Oxygen is a diatomic gas. I'm going to go ahead and put the gas state designation there. I'll put the gas there. Sorry, I got a little clumsy, but oxygen, again, if we remember, wants to have 2 bonds. It can do that by bonding to another oxygen. Oxygen also has 2 lone pairs. These are going to come together and form a reaction. In this reaction, this will not go unless I add heat. The heat to make that reaction go. Or if I add an activation energy, which E subscript A is activation energy. I need to give this reaction energy for it to be activated. If I had a balloon of methane and oxygen, that balloon won't just all of a sudden burn. I have to light it on fire. I have to give it some energy to activate the reaction. And if I do, that combustion reaction, fire is combustion, that combustion reaction is going to make water and carbon dioxide. And water and carbon dioxide are the classic products of combustion reactions of hydrocarbons in oxygen. Hydrocarbon meaning that hydrogen and carbon bound together. Methane would be a hydrocarbon. The water that this reaction produces, remember this is fire and so it's not cold. So this is going to produce water vapor. So water in the gaseous form. And carbon dioxide is also a gas. This reaction clearly also produces heat. It's fire. All right. This is not a balanced chemical reaction. We can go ahead and fill this in with molecular structures. Oxygen wants to have 2 bonds. Hydrogen wants to have 1. Carbon wants to have carbon wants to have 4 bonds. Each oxygen wants to have 1. Oxygens want 2 lone pairs. Everything is happy. The problem that we have is that if we look, the reaction's not balanced. There are 3 oxygens over here and only 2 oxygens over here. There's 1 carbon and 1 carbon. That's all fine. Except there's 4 hydrogens and 2 hydrogens there. And it's a little bit of trial and error. We can start thinking through it. I just kind of go for it. I say, well, what happens if I add a 2 to that there? And I see that that works in some regards because now I have 4 hydrogens. I've added another water over here. And so that gives me 4 hydrogens. I still only have 2 oxygens in my reactants and 4 oxygens over here. So if I put a 2 there, that adds another one of these diatomic oxygens. And now I have 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, and 4 oxygens. Another way of looking at this same reaction, which is a necessary component, is to talk about the potential energy surface. Often abbreviated PES. That can be confusing because PES also stands for photoelectron spectroscopy. But the potential energy surface, I'll write that balanced chemical reaction out as well. CH4 gas plus O2 gas is going to go to make water vapor as well as carbon dioxide. This reaction makes fire, it produces heat, it also takes a spark or some heat input to set it off. And remember that this delta is the one we're calling the activation energy. It's not balanced. We need a 2 there and a 2 there. I'd like to talk about the energy for just a second. That's what the potential energy surface is. When we make a potential energy surface, the vertical axis is chemical energy. Often chemical potential energy. I think it probably is more appropriate at this point to give it its full name. Chemical potential energy, the energy stored in the molecular bonds of the molecules. And the horizontal axis is what we call progress along the reaction coordinate, or I'm just going to call it reaction progress to keep it simpler. The energy here is in the reactants. We know that because the reaction produces fire. And so I want to make sure that the reactants have higher energy than the products. Because this reaction produces heat, it makes fire. And so I put the CH4 plus 2O2 there. Those are my reactants. And then I'm going to put the products over here, 2H2O plus CO2. This reaction has a shape to it. The potential surface has a shape. That shape goes up and then down. Again, we could put exact numbers to these things, and these are known numbers, but I'm not really worried about numbers right now. What I want to talk about is that I know there's a bump there, and I know the reactants start higher in energy and the products end lower in energy. I know this part because this reaction produces heat. That's that delta, and the reaction produces heat. Because the products are lower in energy than the reactants. I also can tell from this potential energy surface that this reaction won't just all of a sudden go. It's not going to explode. It needs a spark. And so that spark has to give energy to the reactants so that they can pass over this hump, which is the activation energy barrier. I'm just going to call it the activation barrier. And so that would be the potential energy surface for this reaction. I think one of the analogies that is quite useful that we talk about is that this, you could imagine just a marble right here, and if that marble was rolling around on the surface, it would have to take a push to get over the hump, and after it did get over the hump, it would fall down quite fast. There's a lot of things we talked about in class, like dropping a bag of sand. We know that the products are lower in energy than the reactants because just like a bag of sand, if we drop a bag of sand, the energy has to go somewhere, and that energy goes into heat, which is quite factual. If you drop a bag of sand, when it hits the ground, it does heat up. This is the potential energy surface for the combustion of methane with oxygen to produce water vapor and carbon dioxide.